We are team number 516, Gears of Fire.
Our team consists of 3 sub-teams, building, programming, and communications.
To allow for maximum proficiency in each of our sub-teams, we dedicated the first 2 weeks of school to teach new members the basics of robotics. Next, we established the difficulty and point value for all the game objectives. We decided who would work on each of the robot's various sub-assemblies and began brainstorming, sketching, CADing, and finally building. We used Google Drive, Google Hangouts, email, and our club website in order to communicate amongst ourselves continuously and store information.
One important goal of our team is to inspire the next generation of engineers by promoting FIRST and FTC in our community. We accomplished this task by organizing outreach events such as National Engineering Week demos, as well as demonstration scrimmages at Raytheon and the Museum of Science and Industry.
The majority of our funds come from grants, fundraisers, sponsorships, and club dues. We would like to thank TBTA, Advanced Systems, Raytheon, Outback Steakhouse, Rockwell Collins, PTC, PCS, and FTC for their invaluable support over the years.
In a game like Rescue, where mobility is everything, without effective wheels, the robot would not be able to succeed. We first tried using the Mecanum wheels from last year. While they performed well on the mats, we quickly found that the Mecanum wheels were ineffective when it came to climbing the mountain. We then designed and created wooden wheels with triangular cutouts to aid in climbing over the churros. Eventually, we found Proline Sandpaws a superior alternative.
During testing, we saw that debris prevented our robot from moving reliably around the field and scoring. Debris would get under our wheels and make a bumpy ride, causing the loss of scoring elements. To solve this problem, we mounted plastic shields onto the robot to keep debris from disrupting the drivetrain.
Another problem we faced was the stability of our robot. In order to fix this problem, we used cylinders of galvanized pipe and rebar that were small enough to tuck away inside of a channel and heavy enough to make the robot sturdy and robust. Finally, our drivetrain was ready for use and worked very well in competition.
To make operation of the robot more user-friendly, we've added 2 helpful features. There is a button on the driver remote that is programmed to slow down the robot by 50% when pressed, allowing for improved control. To avoid having to drive backwards, we added a software switch that adjusts which side acts as the front by reversing the driver controls. An arrow was added to indicate this change.
Early on in the season, we decided to focus on the valuable points that can be obtained in the end game. Developing a pull-up mechanism became a primary goal. Originally, we planned to use a linear slide system similar to those present in forklifts to pull up and hang from the pull-up bar. However, a CAD design quickly showed that the mechanism was too large to be of practical use. Our next idea was a cord winch system. We chose to forego the cord entirely and made a pull-up system out of the tape measure instead. The idea was a success, and our system has enabled us to hang reliably in each match.
To deposit climbers into the shelter, we decided on a simple bucket and arm design. We began by designing the components, first on paper, then with CAD. We started out by making a prototype out of foam board. Unfortunately, the metal construction was too heavy to be turned by the servo. Our solution was to reduce the weight by using a combination of plastic and wood instead. We used sensors for precise movement and control during autonomous mode. One type of sensor we used was a motor encoder, which allowed us to program our robot to travel specific distances. Additionally, we used the robot controller's camera to navigate around obstacles and analyze the state of field elements.